Welcome to the, I guess, second day or third day, depending on how you're counting, of TechEd. My name is Tobias Ternström, and I'm a lead program manager in the SQL Server / Windows Azure SQL database team. So just briefly about us, we're about, I'd say, 500 engineers or so that work on SQL database engine itself. So SQL is split into three parts. We have the database systems group, which is focused on database technologies such as the database engine, Hadoop, and similar things. We have a BI team that is very focused especially on visualizations, and the information services team, which is focused on turning data into information. Each team is around 500 engineers. And my team in particular, we work primarily on SQL DB. Now it's a single main line of source for SQL Server and SQL database. So when we develop for either one, at some point the features are supposed to turn up in both products. And we're slightly different focus depending on what we're working on. And my team especially focuses on, currently it's focused on performance in SQL database. We also own the programmability aspect of the service, but right now the investment is primarily around performance. I'm Swedish, but live in Redmond. Are there any Danish folks here? No? Everyone else is very welcome. The Danish guys invaded Sweden, so I'm always kind of hesitant to these guys. Otherwise, it was typically Sweden who created havoc in Europe, but then the Danish were better at this. Okay, cool. So let's get started. And please, if you have questions, don't hold them till the end, because then I'll be kind of highly confused and be harder for me to get context. So context is good. So just raise your hand if you have any questions, and we'll take it during the talk. And it's typically mostly interesting if we have the conversation during the talk. So what we're going to talk about is what is different in SQL DB and why. It's also to some extent what is different in a VM or in a hosted VM versus running it SQL Server on the raw iron. Cloud optimizing your design. Connection reliability is a big deal. Reducing round trips, caching. So things that make your app work well in the cloud is really what we focus on. And also we start with the aspect about why things are different. So you could argue SQL Server is really, we have three products, or three ways to run SQL, and they are kind of fundamentally different, right? So the upper left-hand corner, you can see on this scale, we have resources, so I/O, CPU, and whatnot, from shared across many tenants or many databases to dedicated resources, right? And the other pivot here is friction, meaning how much work do you have to do to get your thing up and running, right? Or do configuration changes and whatnot, as well as how much control do you get. And it's a bit weird. This one, you can see high is over here. That's someone that works in my team who is he's very interested in PowerPoint. And it's apparently, he likes it when things go down like this. So this is high friction, high control, and over there is low friction, low control. So SQL Server raw iron, that's the normal way to run SQL Server that most of you have done or are doing today. You just run it on the physical box. And there are great reasons to do this, and primarily performance related and availability related. So in the upper left-hand corner, you can buy a huge machine, right? Lot of memory, a lot of cores, and you can run an app there, a database that requires a lot of power, right? And if your app goes slow, right, you can obviously optimize your app, but you can also buy bigger hardware, right? And with the hardware trends today, you can buy very big hardware. So I'd argue most of us wouldn't have a problem running our app on one SQL Server, right, one instance. I think now in 2014 we'll support up to 640 logical processors or something and terabytes of RAM, right? So that's very nifty, right? And what is particularly interesting about that solution is the older the app, the more problematic it is to change, right? So if you have an app that's 10 or maybe 15, 20 years old, you may not have the source code, or the source code is huge and not well organized, or you don't have anyone that understands it. It's very hard for you to go in and tweak and optimize that app, right? So the bigger that one is, the likelier it is that it's going to need to run on a scale-up architecture. And it's important to know that there's nothing wrong with this, right? However, you need to buy a big enough machine. And that's where the problem comes in, because if I want to do high availability, I probably need to buy 2 or 3 of these, right, and set it up, etc. And if I have my biggest load, let's say the end of the month when you do salary processing or something like this, I need to buy a big enough machine to handle that load, right? The next step is, so why would I want to move out of that? Well, it's really the cost thing, right? So it's fine for your one big app, right? But if you go to most companies, they have a few huge apps, right? And then they have hundreds of small apps. And it's very common to have a standard that you get a machine per app. And you then have to set it up and scale it for this peak load. And you end up having to buy quite a lot of machinery and spend a lot of time managing it. So the next step to be able to consolidate is to go and run SQL Server in a VM, right? And you can either run it yourself, and then you manage the hardware, right? Or you run it with a hosting provider, and obviously I'd suggest us, right? Azure, we have GA'd VMs in Windows Azure. And it's pretty cool. We also announced that we're billing our virtual machines at minute intervals, which is very interesting. Obviously, the bigger the machine you buy, you're going to pay more, but you can then give it more power for exactly the time that you need it. So most providers charge per day or per hour, and we charge per started minute. So in a VM, the nice thing is it's exactly the same SQL Server, right? Anything that works in the upper left corner will work in the middle one, but maybe not as fast, right? Especially if it's a big enough thing. If you go, especially with a hosting provider, we sell VMs up to a specific size, and you cannot get bigger than that, right? The nice thing, though, with a VM is you can start running them in Azure, and if you have one that actually needs to be bigger and it's an old code base, you can't change the app, you can obviously just download it again, right, and run it on your own, either on your own hardware or run it on the raw iron, right? So that's an important thing with this whole hybrid cloud thing, is to be very pragmatic, right? There are lots of people saying, oh, you have to go this direction or that direction, and that's typically not true, right? There are a lot of companies that have set in rules that say you're not allowed to buy hardware anymore. But that's typically to make people try to do the right thing of try to use less new hardware. And obviously, as time goes by, we upgrade our data centers and buy new SKUs, new hardware SKUs. So the cloud providers always upgrade, but obviously, if you run SQL Server yourself, you can always buy the latest hardware, and you can get it, tomorrow. And then we have SQL DB, which is these two up there were, machine and the virtualized machine. And here, instead of virtualizing a machine, we virtualized a database. And there are a few different reasons why we did this. Primarily, the instruction set is far smaller, right? So here, what we give you is a TCP connection that you do TDS over, tabular data stream, and you speak SQL to us, right? So the instructions that we have to provide is T-SQL. In the middle one, we have to give you a full machine, right? So in the lower right corner, I can go and do things because of the reduced instruction set that basically make it cheaper to run. For example, a VM has to be running all the time, right? If it's on, and you pay for it. You could imagine a database, if no one is doing any requests, it's just storage, right? So it doesn't have to be an extra machine running. With the lower right-hand one, you can probably have hundreds or even thousands of those databases on the same physical hardware, and then do work to load balance when the databases become active, right? But because we decided to do a database the instruction set is smaller. It's not exactly the same as SQL Server in a VM or in raw iron. So, for example, you don't have agent jobs. You don't have the MSDB database. We don't have service broker enabled right now. We don't have distributed queries enabled. There's lots of things that are not enabled. Some of them we're working on enabling over time, and some of them not, because they don't fit the model of there is a database that's the unit versus there is an instance that's the unit. Okay? But the interesting thing is here is these are fundamentally different things and are good for different things. The nice thing with the database is obviously, if I need a new one, my typical demo, I'm not going to do it here, but is you connect with Management Studio or whatever, say create database to BS1, and then you have it. You have a database that is highly available, so we keep 3 or 4 replicas of your data on different machines in different racks in our data center, and all you had to do was say create database. When you don't need it anymore, you say drop database, right? And right now you pay only for storage, right? So if I need 500, I say create database 500 times. And I have 500 now highly available databases that are backed up, maintained, and all of this for me. So from an app perspective, there's much less time you have to put into the whole maintenance of your app, and you can focus more on what actually is the queries that you need to run. This is just briefly talking about the same thing that I just mentioned. So, and this is also fundamentally different, right? So this is what you guys are typically used to. You buy enterprise-grade hardware. How many have a SAN? Most of you. How many like the SAN? Okay, 10%, maybe 15%. Yeah, SANs are problematic. They're typically great if people set them up correctly. But it's funny, right? In most companies, you have the SAN team and the database team. And there is some big wall in between them. It's very common, like, I need some storage for my DB. And the only thing they typically tell you is, yeah, how many gigabytes do you need? Like, I don't care so much about my gigabytes. I want a certain throughput of I/O. No. It's a SAN. It's super fast. And then, yeah, you run into trouble. But many of you have, SAN set up the right way, or local disks, SSD drives, the best switches you can buy, all of these things. So it's extremely stable, the hardware infrastructure itself. But it's obviously expensive. You have to go and buy the right things all the time as you upgrade. The point for all cloud providers, independent of if it's us or others, is that we buy commodity hardware. Now, the term is it's not like it's the absolute cheapest things you can buy, but definitely it's not the most expensive enterprise-grade hardware. So we buy a box, and we buy lots of this one box, right? Lots and lots and lots of them, thousands of them. So get good deal, right? Get good price, and maintenance gets much easier, right? You can make a deal with Dell or whoever and say, oh, okay, this one is bad, you come and switch it out. We have everything is the same. But that also means, because we buy the cheaper hardware, it's not going to be as reliable as if you buy the super enterprise hardware. Instead, we build software on top of this to make it as reliable as possible, right? And it's very much you get what you pay for, right? If you buy the most expensive Azure subscriptions, you'll get, for example, your own machines that you run on. Versus if you pay us, $2 a month for something, you're going to get, less, right? And that's very important to think about. So it used to be the way that if I build software on the left-hand column, as a developer, I don't have to think all that much about performance. I know a lot of you do, and that's good, right? But you don't have to think about it as much because you over-provision hardware all the time. So if a data center runs at 10% utilization, typically you say it's pretty good, which is horrible, right? You spent €1 million and you only got 100,000 euros worth. So in the cloud, all of a sudden, it's very transparent how much money are we spending on a particular app, right? Because those are the databases for that app, those are the VMs for that app. So you get much more interested in writing code so that you consume what you need. And the more resilient your app is, the cheaper you can run it. So that's very often the game. And you can start with building it, I'll provision big VMs, And then you can start, okay, what happens if I go smaller and smaller and smaller? And at some point you'll find, ooh, now we're running into problems. And then you can either fix your app to make it behave nicely in the environment or pay more. So it's very pragmatic that way. But you have to think about it. And this is just touching on the subject I said, and this is true as much for SQL Server as it is for SQL Database in Azure. If you have a database, create a database. It's just an MDF file, an LDF file, but it has a bunch of leaks, right? It uses things that are instance-wide, like you see here, agent jobs, replication, database mail, instance collation, we're dependent on logins, credentials, TempDB collation, you may join other DBs and whatnot. And this is true in SQL Server. If I want to move this database today to another server, well, those connections won't be there, right? So I think a lot of you probably run into this. You want to move to a different server, and now you have to make sure, oh, which are the agent jobs, which are all of these things. That's something that you have to think even more about when you go into the VM world, because even in VMs, you will be much more interested in moving your databases around to basically pay the least amount of money possible. And in SQL DB, the nice thing, you can obviously say it either way, right? But the nice thing is we force you to do this because the abstraction there is the database. So it's always like this. We don't allow you external dependencies. The only thing that's external is logins. You create logins outside of the database. And firewall rules. And this is also what we are working on going forward. There is a feature in SQL Server 2012 called contained databases, which changes the behavior of a database slightly. For example, we are not dependent on the TempDB collation anymore and the instance collation. That becomes the server the same as the database. And a bunch of things all of a sudden become local to the database. But in this version, we only have what we call partial containment. Let's see if I can. Just show this. So I go properties on this database. And you see we have containment type there, and it says none. You can switch it to partial, which means it's, roughly half the way to Azure. Azure is strictly contained, meaning you can't go outside the database. Partial means we change the behavior slightly, and you can detect through certain DMVs and catalog views that we have if you're breaching containment, but we don't stop you. Okay? So it's very useful actually if you're moving your database around to have a look at this partial containment, because it can help you find out what external dependencies you have. Obviously you don't know the ones going in, like agent jobs, but you know the ones going out. So we think a lot now about database features, what things are local to a database, like tables, triggers, all of the common stuff. And some things are host specific, and those you have to think about when you move your database. What high availability solution is available on the other server? What instance collation is available on the other server? How are backups used there? All of those things. So that's an important thing to think about when you plan your setup today. And we have some iffy features, like create database itself. You would argue is it a database feature or a host feature? It's one of these in-between features, because, for example, you specify which path it is to the files, and you create database on that specific host. But overall, going forward, we focus the development very much on the left side, right, for developers. It should be database-specific features rather than things that you have to create in the host. So, we're going to talk about a few best practices, and these are the same independent of if you run it on raw iron, on a VM, or in SQL database. These are things that you want to consider either way. And obviously, even if you run on raw iron, it's good if your app is prepared to run easier on SQL DB, or run better on SQL DB. So first of all, it's instrumenting your app, which is super important. So can you get the telemetry you need to understand, is there a problem, and what is the problem? So we'll go into a few details there on the next slide. Automate, automate, automate. That's also one of these things. Overall, if you have just one server and one database, life is good. right? You can, sit and work with that. You can sit and look at the screen, things, what's going on. But as soon as you have 5, 10, hundreds or thousands of them, more and more has to be automated. And if you look at, I'd say, many customers, it's typically the level of automation stops at some point because people say, well, okay, we automate backups, we automate this and that. But there are way more things that you can automate. Way more things typically. So that's a very good thing to think about, is what can we automate? And can the application take actions to fix problems itself? The more you do that, the more you can spend your time on important things like root cause analysis of actual new issues that you don't know about versus spending time on, yeah, okay, this has happened again. Okay, I'll have to go and do this same thing that I keep doing. So that's definitely worth thinking about. And this is something where we spend a lot of our time when we run Windows Azure SQL database. It needs to be fully automated, right, to handle things like load balancing between machines, obviously backups, alerting on performance, lots and lots of these things. Obviously, we're not going to talk specifically about that, just a little bit, but in this talk, there are other talks about optimizing database design and queries. So obviously, the more efficient your queries are, the more you have the right indexes, the less hardware you can buy, right? And the cheaper and better your app will run. Make your app resilient to failures. We'll talk about this in a bit, especially when it comes to connections. And minimizing round trips, which is also very much about performance. The lower number of round trips you have to the database, the better your app will perform. And typically, you'll have less problems with failures as well. So first of all, instrumenting your app. This is, and there's lots of software that you can buy that helps you do this. Most of the time, you'll want also to do some of it yourself. Independent of if you buy or do some of it yourself, it's interesting to understand what actually goes on under the covers. The more you spend your time there, the better you will be at fixing issues with your system. So we have a white paper that I will mention that is worth reading. Windows Azure SQL Database and SQL Server Performance and Scalability Compared and Contrasted, that a few of us wrote. And it has a lot of the explanation, some of what I've talked about here already, but a lot of the actual things that you should think about when you, let's see where it's recommended performance evaluation techniques, like what should you do to understand performance in your app. And it has some sample queries as well against DMVs and whatnot, so what you can do both against SQL Server and against SQL DB. So this one is worth having a read through. It's a bit elongated, but it's very American, so you need to write a lot. So how many of you have used DMVs? About half. So DMVs are basically dynamic management views, it's short for. And it's a way for you to query into basically SQL Server metadata to understand what's going on in the service right now. And these can be very useful to debug problems on the spot, right? You connect and you say, oh, what's going on? But they can also be very useful to understand, to basically retrieve information from periodically to understand trends and what's going on in the service so that you can detect problems automatically. The other thing that is super interesting that I don't think most people have worked with enough, we released this in SQL Server 2008, is X events. How many of you have used X events? Only a few. So X event is really our replacement for trace in SQL Server. So today, I'm guessing a lot of you use Profiler, right, and Trace. So X events basically are way lower overhead on the service than Trace, because it sits at different places in the engine. And you have much more objects that you can basically trace on. The other thing that's very interesting with it is there's a framework so you can set up an X event and say, I want to listen to when some OS task finishes, okay? You set up that, and you can then say also where, the elapsed time was longer than this and that was true. So you only capture what you're actually interested in. And you can capture both to memory so that you can just query it locally, but you can also capture to a file. And you can tell us to, generate a file every 10 megabytes or whatnot, which means it's very easy for you to then grab those files off of the machine and put them into a data warehouse or into some place where you can query what's going on. So that's also a lot of what we do for you behind the scenes in SQLDB. There's a bunch of X events going on. We collect it from the machines, we process it, and we look for trends and alert on trends of what's going on in the system. Lower overheaded X events, yes. And as with everything, when you monitor it, it's good for you to look at, okay, I turned on all of my monitoring, what was the cost for this? Was it 1%, 0.5%, 10%? Because I'm sure if you turn on everything, then obviously you're going to have a ways overhead. And also your files will be big, and it will be hard for you to understand what's going on. So this is just some examples. So one here is an X event SQLOS.waitInfo. Overall, when you're performance tuning SQL Server, wait stats are super interesting. Right? So typically what you look at is utilization, which is how much hardware goo did you use, right? How much CPU, how much I/O, and whatnot. The other thing is latencies. So how much time did I have to wait to get that I/O, to get to run on the CPU and whatnot. So looking at wait stats typically tells you a lot more than most of the other things, because that tells you what SQL Server is waiting for, right? So if you want to use the X event, you can use this as one of the X events where you can get wait stats. If I just query this view, this is one of the DMVs that has wait stats. You can see here that it will give you the wait type, which is really like a semaphore in the engine that we say, some developers said, oh, I'm waiting for this, and then they define, okay, this is what I'm calling my wait. None of them are covering, so each wait it's actually waiting for this. It's not like, oh, this wait actually contains this and this other wait, right? So if you're saying I'm waiting for SOS scheduler yield, you're waiting to be scheduled to run your thread, for example. So for example here I can say, oh, okay, we have some amount of wait for locks. And lock is one example of, it's an app issue typically, right? Your app is waiting for a write, to be able to write or something like that. So you may want to look into using, I don't know, read committed snapshot isolation or read uncommitted or whatnot. If I go down here, let's see. We have, for example, these page IO latch waits. So page IO latches, I'm waiting to get a page, 8K, into memory from disk. So if you're waiting a lot on that, you're waiting a lot on reads, right? Take some other one here. And we have about 250 of these, so you're absolutely not interested in all of them. SOS scheduler yield, so yeah, waiting to be scheduled. And the other thing that's also interesting actually is this one, signal wait time. That is, so the wait time is the total wait time. Max wait time is the maximum for a single occurrence, right? Signal wait is how much did you wait before you could actually wait. So that's waiting to wait. That's waiting for the CPU to acknowledge that you want to wait, right? So typically, CPU, you would want to look at SOS scheduler yield as well as the sum of the signal wait, right? To see what your problems in CPU is, what your latencies on CPU is. Let's see. Obviously, you have backup. You have lots of these things here. See if there was one other to mention. The other one is write log, is worth mentioning. Write log is obviously you're waiting to write to the log. So that's typically what you say write log is for writes. On SQLDB, there is also wait types related to, so in SQLDB we have these 3 to 4 replicas. And we have to do synchronous writes to at least one of them. So we have them waits for, it's called SE REPL commit ACK. and rollback ACK. So you're waiting for the secondary to acknowledge that you wrote. We also have something that's called SEREPL slow secondary throttle, which is the secondary is overloaded. It's too many writes happening, so it's telling the primary, don't write for a while, right? So overall, these are very interesting for you to look at to understand what's actually going on. And you just need to go and Bing for wait stats and SQL DB or SQL Server, and you'll get lots of information about them. But this is just to trigger kind of the interest. The other thing that you can do with DMVs is I can obviously snapshot this DMV, let's say every 5 minutes. So these are always cumulative and get reset when you restart the service. So if I requery this every 5 minutes or so, I can see what the differences are and I can develop a trend. So what are my problems? And obviously, you shouldn't be too quick to judge. For example, if you're waiting a lot on page IO latch, on reads, you may not have enough memory, right? Because your working set doesn't fit in our buffer pool. And I don't know if some of you went to the hackathon or in-memory DB talk yesterday. If you run hackathon, you won't have page IO latch, right? Since we're always in memory. And then, yeah, the other one here, this is just another one to show. And again, in that white paper I mentioned, there are a bunch of these. In here, this is statistics for each query that we have in the procedure cache. So this one also is super interesting to look at without having to start a trace or X event session or anything. You can see that whatever this particular query was, it was executed once. It spent 228 milliseconds doing CPU work and didn't do any physical reads, any writes, and so on. So here you can see at the query level what's actually going on. But it is important to note that if your procedure cache if things get ejected from the procedure cache, they disappear from this view. Right? So these kinds of things you want to automate so that you can understand what's going on across your whole system, right? Versus having to go. It's also very good once I know there's a problem here around CPU, okay, I'll look at the queries. But you want to automate so that you can actually get to that fact very quickly. So connection reliability. Again, this is especially important in the cloud just because of the fact that you run on commodity machines. For example, in SQL DB, just as an example, the cheapest DB you can get is $5 a month, right? And that's $5 a month for a highly available database with 3 replicas in our data center across 3 different of these fault zones or 3 different racks. And because we automatically load balance, we may decide at some point, ooh, this machine is overloaded, we need to move your database over here instead. So we'll disconnect you, right? And you'll have to reconnect again. This is also true for VMs to some extent, right? And it all depends on what you pay at the end of the day. So if you're going for a cheap app, this is very common, right? If you imagine Access is built this way, for example, in 2013. If you create an Access web app, it's called now, that's the new type of Access apps, you get a SQL DB database, right? So every Access app you create through Office 365 is a SQL Azure database in the back end. And that's super good for them development-wise, right? The only thing they have to do to get a database to run Access in is, say, create database. So they create tens of thousands of these databases. But obviously, then Access team is very interested in, can I please run these databases, depending on the customer, maybe on what subscription they have with Access, at the lowest possible cost, right? If I'm going to have tens of thousands of databases, it's very much an ISV kind of scenario. I don't want to pay lots and lots of money for each database, right? So when you look at this typical app, you have the scenario, there's the user that wants to do something, right? So he uses a client app, probably Internet Explorer or something like that, communicates with typically a web server, right? That communicates with a database server. And what we say is everything, I'm not sure if the user is not durable or not, but typically you say all of this, including the database, is unreliable, meaning that internet can go down, User, I guess, can forget what's going on. Definitely, his PC can run out of battery or something like that. Web server can crash. Network can crash. All of these things. So the whole thing is unreliable, right? Then it's a question about frequency of unreliability. But everything can fail, right? The durability, meaning did you forget what happened, right? Database is typically the only thing that's durable. Your web server typically isn't durable. If you reset it, it doesn't remember anything from before when it was started, right? Same with Internet Explorer or your typical client app. So this becomes a conundrum when it comes to communication, especially with regards to writes, okay? So like my typical example is, let's say I build a feedback form, right? I want to provide feedback for SQL Server. So there is a text box where you provide your feedback and you hit submit, right? Well, that's sent to the database server we're putting it in some table, okay? Now, when I do that, let's say I click submit. Now, obviously, Internet Explorer will start waiting for the response to come back. And you have probably written maybe some JavaScript, right, that says, okay, submit this. If it doesn't come back within a certain time, what do you do, right? Well, one thing is you can just say, oh, failed, and it's back to the user. What can the user do? Well, he can hit submit again. Now the question is, when he hits submit again, or maybe if your JavaScript says, okay, I waited 5 seconds, didn't come back, I'll just submit again, right? Will it end up twice in the database server, or 0 times, or once, right? Will there be duplicates in this feedback? Because this is a typical example of an operation that's not idempotent, meaning if I do it twice, right, it's going to be happening twice in the server, right? So I can't just run it 10 times and the original state will still be the same. And that's an important thing that most of us didn't have to think about when we ran in this enterprise-grade environment where we're always running in extremely reliable hardware, and it's our own hardware, right? Only my database runs on this hardware. So if you look at this, it's now, so it used to be this way always from the web browser, right? So banks, especially bank apps, has to think a lot about this. Order apps, you're used to this. If you order something online, it says, oh, don't hit submit again. Wait at least 50 minutes and then maybe hit the submit again. But now all of a sudden it becomes more and more interesting from the web server to the database server, especially if you want to run your app in a cheap way or your app supports running cheaply, because then your database may be moved around a lot more, right, because of load balancing in the data center. So how do I do retries? So first of all, one thing that can happen is the connection to the database server was dropped, meaning the send didn't go through. Well, in this case, it's obviously safe to retry, right? I'll just send my insert again, and if it works, it worked fine, and that's just one instance of my feedback, right? However, what happens if it didn't get back, right? Which is also equally true that it can happen. The send went through, but the response from SQL Server didn't get back to the web server. The web server can't see the difference between these two, right? It's just, I didn't get the response. I don't know if it reached the database or not. So he will always want to take the same action, right? I want to retry this. So now the question is this retry safe or not, right? And this is obviously only something that you need to think about. One is if your statement or your operation is not idempotent. So for example, all read operations doesn't matter, right? Okay, I'll just read again. Write operations, it depends what type of write operation, if it's idempotent or not, right? So let's look at an example of this first. So this is my little app. So I connect, I do a begin transaction just explicitly in the client API, just to be clear. Then the only thing I'm going to do is I'm going to update accounts, and set the balance to minus equal to 50. So I'm taking out 50 euro out of account ID 1, right? So I sent the begin transaction. I can see in Profiler, right, we got a transaction starting. I send my batch. We see that the update happened. Now, when I reach commit, right, now, let's say I have a try-catch around all of these. If I'm around the begin, I know I can just retry, right? If I put my try-catch around the update, I know I can just retry because it was a rollback, right? It's guaranteed to have rolled back, so it's safe to retry. But what if this one doesn't come back, the actual commit? Or if I just executed the update, so it's an implicit transaction. Is it safe to commit to retry or not? So typically I would, there are frameworks that do this for you, but I would have some sort of while loop around this, right? And say, oh, if there's an error, retry, depending on the error number and whatnot. But here I won't know if it's safe to retry. Because what happens in SQL Server is we get a commit token, we commit, and we send an ACK back. But then we don't wait for anything to come back to us again saying, oh, I got your ACK, right? Because that's fairly inefficient, right, if that happens for all transactions. So we are done, it is committed, but the client app may not know it's committed. So now if you go and retry, you may actually extract now 100 euros instead of 50 euro from the account. Make sense? So we got the commit. So what can we do to make this safe? And again, you would only do this where you're worried, right? When you think this is a problem, if it happens in your app. So the protocol, the algorithm that you typically use for this is just another handshake, basically. So the client assigns a unique identifier. You tag the request somehow. And a GUID is typically a good idea. So you tag your request. You send it to the server. The server always checks, do I already have the request? If I have the request, it means it already happened. So this is important to understand. This is not about a transaction, right? It's about, did it already happen or not, right? Is the transaction already committed? Is it safe to retry or not? So if the request already exists, the server will return an error to the client saying, no, 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 I'm already done. Whereas the client will exit the loop and say, okay, don't need to retry. Make sense? So if it's not there, then the server will begin a transaction. It will save the request ID. It will execute the request. It will commit the transaction and return the result. Right? So now, when the client receives the notification from the server, the only thing the client does is send, okay, I'm done. Forget about this request ID. Right? And the nice thing is, this delete, this is an idempotent operation. So if the client, if this one fails, it can retry and just delete as many times as it wants, or you just have some, probably you will have some retention cleanup. So you clean up all the request IDs, request IDs that are older than an hour or something like that every now and then, right? But this means it's safe. The client will always know, or that the server will always know if this request should be carried out or not. So So just look at a simple example here. So I have this accounts table. And then I want to manage these requests. And I think let's see if I created a requests table already. Yeah. So I have a requests table which just contains the GUID and the date that the GUID was created so that you can do retention cleanup, right? So the protocol would be something like this, right? On the client side, you get your GUID or whatever you want to use, right? Could be some sort of hash. And then on the server side, you would have always a transaction, right? Because you don't want if something happens, you obviously want the whole thing to roll back, including saving the request ID. So I have a transaction. And for simplicity, I'll just say set transact abort on, which means if there's any errors, just fail and roll back. Then the first thing I do, and there's various ways to do this, is I check for the request ID. And in this case, since it's a primary key, right, the request ID, I'll just try the insert. If the insert fails, I know that the request is already there. So insert requests. And here I'll pass whatever the client sent, right? And in the catch block, I'll just throw an error and say, okay, already done. And I will roll back the transaction. I don't need to roll back the transaction here since okay, I'll not run this now just so I can step by this. So I'll roll back and throw this exception. Or actually, well, if you're in set transact abort on, you don't need to do the rollback because the rollback will happen when you throw. Okay, so that's the initial thing. After I check this, now I know it's safe to continue, right? I know this hasn't already happened. So I can say update test accounts, set balance. We'll just hardcode this. And then the last thing that will happen is that the client again will say delete request where ID is equal to the ID, right? So if we try this, just get the GUID. And first I'll just pretend I'll step through it. So I'll say begin transaction, we'll insert it, and we'll pretend this failed, and roll back and throw. Now obviously if I query test requests, the request ID won't be there, right? Okay, so, but we'll run this. So now we're in the, end catch. So we're in the transaction, we save the request ID. Now let's say something goes wrong, right? So we get an error. Now again, the request ID isn't there, so we know it's safe to retry, right? But if we go through the whole thing, now it's happened, and the request ID is there, so if the client now retries again, he gets this error back. So we know it's idempotent, and now the only thing the client needs to do is to send the delete. And obviously, after the client sends the delete, it could happen again. But it's obviously this instance of the client will not retry, so it's safe. You can also only do the retention cleanup, but that will not be as efficient. It's better to just always do the cleanup. And do note that this protocol is good to use even if you're on the enterprise-grade hardware in your own data center. Because if you have these operations that you need to be able to retry, right? Because you can also want to retry just because of the fact that the application server went down, right? And you say, okay, now we need to retry. You need to have a protocol so you know that it's idempotent and it's safe to retry. Make sense? And throw is new in SQL Server 2012. So retry considerations, again, reads, just retry. There's no problem, right? Writes, if it's not idempotent in itself, right, and you're worried, let's say there are lots of write operations where you don't really care, right? If it happens, if it overwrites data, or if it adds data twice, then it's fine, right? But when you care, it requires tagging of the transaction. It requires some sort of handshake. Then there's also the fact that there is low-cost and high-cost operations. This is super important if you want your app to be resilient and actually perform well. So simple low-cost operations, it's obviously safe to retry quickly. Just, okay, retry, lots of times, and then maybe wait a little bit, retry. So you have some sort of general backup mechanism. You retry after immediately, right? Then maybe you wait 10 seconds and you retry and so on. But for high cost operations, this can bring your database down, right? And it's actually fairly common that you see this. The database server is overloaded, or there is some bug, right, that you hit. And now all of a sudden the app just pounds the server with requests. And the server dies, right, from this, or gets unresponsive. So that's important to take care of as well, like to classify, is this safe to retry based on cost, as well as based on item potency. So reducing round trips. One thing is, obviously the lower number of round trips you have, the better your app will perform. This is especially true in things like Windows Azure, as well as our competitors. Because it used to be your database server is here, expensive network, or just direct cable more or less, and then here's your web server or app server or whatever. Now that's not true anymore, right? Because there can be quite a few hops between your database server and your app VM, right, or your app server. So, and especially if you run the database or something in Azure, but you run a local client app, then it becomes even more important to not do a lot of round trips. So the classical example is obviously, lots of the old apps do a lot of cursors, right? You open a cursor and you request row by row. That will just kill you in the cloud, right? It will perform horribly. But even if you do execute a bunch of select statements, it's better if you could execute just one and get all of the results at once. So if we look at an example here, let's say I want to get orders and order details, right? What I can do is, let's say someone wants an order, so I would get the order metadata, the order as well as the order details data. So I'll do probably left outer join, sales order detail. And then let's say we wanted sales order ID, order date, and then let's just say we wanted quantity and product ID. Oh, sorry. And let's say we want it for 2 orders, so where SO So this is obviously one way to do it. Now I get all of the data I need, I get it in one request. I could add order by and so on. And this is absolutely a good way to do it. It's efficient and whatnot. The thing to remember is that you have to parse it correctly on the client side, right? You have to figure out that, okay, a certain number of these order rows actually belong to this order when you create the structures on the client side. So you'll probably instantiate some, I don't know, order object and order item object, and you'll populate it with data, right? Another way that's interesting to use is to return XML. How many of you have used for XML in SQL Server? A couple of you, okay? It's actually very powerful and performs very well, especially just retrieving it. So what I could do here instead is I say for XML path and say, okay, for each row I want an order element. And I want a root element called orders, for example. Let's just do it this way first. So you'll see each row, it became kind of a tabular XML structure, right? Each row, and it didn't help us much. You get 1 row now per order item. What I could then go and do is say, okay, I want to actually request the order details separately. So I'll say select these 2 columns. And I'll just call this, I'll add an at in front. That means it will be an attribute instead of an element in the XML. And I add the product ID and I call it, oh sorry, that should be quantity. And I call it PID. There we go. from sales order details. So this is just a correlated subquery. Now this will get all of the order details for that particular order, right? And then I say for XML path here as well, and this is an order item. And I have to say type. This has to do with backwards compatibility from 2000, but now we return an XML type instead of a string, basically. So let's just execute this one instead. And then let's also change this. So I call this one ID. So now I get an XML structure that looks like this, right? And this is now much, much easier to parse on the client side. So even if you use JSON, for example, you could easily restructure this XML into JSON on the client side with much more generic code than what you would have to use to restructure the result set that we sent back. So this is an interesting thing to know about. Any questions? And this is also available in SQL DB and since SQL Server 2005, so it's nothing super new. The next thing is when you want to send a batch of data to the server, and then we have basically two overarching ways of doing it. You send everything, you send one request per thing you want to save, for example. So I want to, let's send save order items. I'll send one row, or I'll execute a statement for every order item I want to send, right, or save. Or I execute less than the number of, less statements than the number of items I want to save. We don't note that we don't say n equals to 1 in the, or n is 1 in the second example, because let's say I want to save 1,000,000 order items. I probably want to batch it, so I send 1,000 at a time or 10,000 at a time or something like this. But this greatly reduces round trips, and performance gets very, very different. So I'll just show a couple of different ways of doing this. So first, you have the round trip per execution. I'll just show this one very quickly as the basis for this. So this basically is this, right? So what I do in this example, I open just a text file that looks like this. And for each of these rows, I want to insert. Now, in your typical example, it would probably be structures that you have in memory or in a data table or something like this, but just as an example. So what I'll do is I'll read through the text file, and then I'll want to save it. So in this case, I apparently here we go. I read a line from the text file, I gather the data, and I execute the query, right? So in this case, if we look in Profiler, this is what happens, right? I get a begin transaction. Begin transaction can actually help performance, because if you do individual transactions, at the end of each statement, you force us to write to disk, right? Because we have to persist the information. When you put it in one transaction, I don't actually have to write to disk until either my log buffer is full or you issue the commit, because that's when I can't lose the data anymore. So that's a good thing to think about, that using transactions can actually help performance. But you see, okay, we execute, this is lots and lots of round trips, right? The other thing that you could do, okay, it's not in the list, is to just build a string with everything in it and send it all at once, which is actually pretty efficient, but it's not very nice code, and you can run into lots of problems with SQL injection and whatnot. So what I can do there is, if we look at the code, I now read through the file, but I append everything, I build up the statement and I append it to a string, and then I just go and execute the statement after that. So here you see instead, it looks like this. It's just begin transaction, and then we get one batch with all of the commands at once. So it's now one round trip, but many commands that ran. The limited list is basically when I create this, I just pass basically the text file to SQL Server, and in SQL Server I go and break down the list into a table structure. And I'll show this mainly because it's a bit interesting of what you can do in SQL to handle strings if you need to. And it's fairly efficient. This is nice because now I don't send a statement, right? I don't send a bunch of statements. I just send the data, which means I'm not vulnerable to SQL injection anymore, right? The only thing that happens is you split up the data and you insert it. You never go and execute it. So I'll hit 3 instead, and then it looks like this. So what I sent now was run this stored procedure, and I just passed the string, right? The whole text file. And then it's up to SQL Server to do something with it. So we can see here, it would be something like this, right? So I get the text as a string. And I have a split function that we created in CLR. There are lots of examples if you go on Bing and search for split strings in SQL. There are lots of efficient ways to do it. So I'll run this CLR split function that takes as an argument the string that we want to split, which is values in this case, and then the delimiter. So first I want to split it on carriage return line feed, right? And this is the rows. So let's just do this to the function. So now this is what happens, right? The split function apparently returns a row ID, and then I get, this semicolon separated data. And now, since I now have rows, right, I can go and apply and say, okay, for each of these, cross apply is run a function or run a query for each of these rows. So run split again, right? And now split rows.value. So that column, split that on semicolon and call that columns. So now I get another row with the data for each of these, and then I can go and use pivot to get each of these columns represented as a column instead of a row, right? But just as an example of that, you can efficiently split a string in SQL Server. Huh? Good question. So we have XML as well. So you can pass XML in there. XML is not as efficient if you send a big chunk of data as other examples. But XML is very, very easy to use. So we see it used a lot, and I typically recommend it. If you're not after the absolute highest performance on the database side, and it's not like it's slow. It's way faster than doing single statements, right? Then you should definitely look at using XML. And that would basically look like something like this, right? You'll send the XML in, and what you would do in the procedure is just select from this XML variable, and note that the parameter is typed as XML, and there's a function there called nodes. So I'll say, okay, please get me all products. So this is just an XPath expression, meaning each of these elements that match this expression will become a row, and we'll call this the XML table with an XML column. So now this xt.xc, you can go and query and get the data. So I'll just say, okay, give me the value of price, let's say. So give me price as type money as price. So now, sorry, XML is always case sensitive by definition. So we grab it, and there we go. Okay? And this is, again, it is very efficient for smaller data sets, but if you're bulk loading large amounts of data, it's not the most efficient. Now, the nice thing with XML is that it's very flexible. So obviously, if they start sending more attributes or more elements or anything like this, as long as they don't change the structure, change the existing ones you're using, it will continue to work. And we also support XML schemas, XSDs in the engine so that you can have it be verified. So that's a very nice part of the XML support. And finally, if you're after the best performance, it's not as flexible as XML, especially you can't pass hierarchies, right? Which is nice with XML. I could pass order with order items, and in one procedure call I could insert the one order, and then I could insert the order items after that from the one XML document. But this is basically you pass, it's called table value parameters, so you pass basically a tabular structure down. And this is super efficient because all we do when we send it is we send some metadata saying, okay, first, each row will be 4 bytes of integer, and then it will be a variable string, and then it will be 8 bytes of money, and then it will be X bytes of something else, and then the next row. So when you send this, it's very, very efficient for us to read this off the wire. So what happens on the server side when you send this is we create a temporary table, and we start loading it. And as soon as it's done, the temporary table is full, we go and execute the rest of the code. So it's super, super efficient, the absolute fastest way to send data to SQL Server. Now, if you look at the code for this, you first have to create a table type. So this is where this agility comes in. XML is very nice because you can just change the definition of the document. Here you have to say, okay, I have a table type that takes these two columns, right? If I need to change it, I need to drop the type and recreate it. And then it's obviously important that you take care about nulls and whatnot, because if you add more not null columns, calls that are executing right now that aren't sending the other columns will fail, right? And the structure must look the same across the client and the server. So there's a bit of a versioning problem here when you upgrade. You have to make sure that the clients has this type defined. So we create the type, and now in the stored procedure, the nice thing is this is the only thing you do, right? You select from this table value type and insert. And you note also that we specify the table type, and we have to say read-only. So basically, we don't support kind of reference type or output parameters for TVPs, right? It's only passed in, which also makes it efficient. If you pass this between stored procedures, we don't have to copy the data. We just pass a reference, say, oh, this is the temp table. If you pass XML, for example, between stored procedures, we have to copy the XML in each instance. And let's look quickly on the code side. So there's two different ways of using TVPs. One is this, which is I create a data table, right? And then I add the columns to the data table, and it just has to match. The types have to match what I have on the server side. So when we send the data, the server will check, does the metadata that comes over TDS match what I have in my temp table? And if it doesn't match, we'll throw an exception. We read all of the data, we read through the file, and we add the data to the data table. And after that, we open a connection. We say that we're going to run this stored procedure. We say that we add the type, and we say SQL DB type structured, and I say the name of the type so that we can send the name over TDS and the server knows what to check for, right? And then we just say pass the data table. So this is the easiest way to use TVPs. Now there is a downside to this that I want to show. So instead of sending this small file, I have a little bit bigger file. So let's start this. And let's just check how much memory So I'm currently using apparently 3.4 gigs of memory, right? Now I say, okay, pass this TVP, which means I read from the file, put everything into the data table, and then send it. So you'll see now how I start using much more memory, right? So up to 4 gigs or whatnot. So the way it works right now, right, is I upload everything into memory on the client side, I send it over the wire, everything into a table on the server side, and then my stored procedure starts. So now it's not streaming, you could say, anywhere, right? It's into memory, everything, then over the wire, into memory or into a table, and then execute. The other way of doing this is using what's called a streaming TVP. So here, I specify I want to run my stored procedure. The parameter looks the same. It's still DB type structured and the same table type. But the value is not a data table anymore. Instead, I've created some type that I call streaming TVP. Streaming TVP. And apparently, I pass a reference to this text file I'm going to send. And then I execute. So if we look in this file, what you have to do is this just has to be a type that implements IEnumerable, meaning it's enumerable, over SQL data record. Okay? So the only thing I do this is I pass in my reader, and then in the getEnumerator method, I instantiate one record that I'll use to send. So it will be only one record in memory in my type. I open the file, right? And then I get the data, I set the values for the record, and then I yield the record. So now what will happen when I execute is the SQL client driver will execute my type, right? It will go in and move next a couple of times to get X records until it fills its buffer. Then it will send it over the wire. It will go into the temp table. Then it will get the next set, send it over the wire, right? So now all of a sudden SQL client handles this whole batching thing for me, right? So the only thing I load into the memory on the client side is whatever I need to. So if we start this again, and now we're apparently using 4.2 gigs of memory, 4.3, and I do the streaming TVP instead, you can see that it hardly moved, right? Because the only thing was this buffer that SQL client used. And it's way more efficient because obviously I start sending earlier. Right? As soon as the buffer is full, we send. So it's going to be faster, but on the other hand, I had to go and implement this class, right? Which it's not hard or anything, but it's something you have to do. So basically, that's why we support the two ways. Either you create a class, and there's lots of examples on the internet of this, that implements this IEnumerable, and you just pass that value, or you use the data table. So, finally, we have 1 minute 38 seconds. Perfect. No, question. Okay. Huh? Oh, good question. What about bulk copy? So, we also have a bulk copy API that you can use, SQL bulk copy. And we have some issues with it right now for SQL DB that we're fixing, but it's not it's a bit more restricted to what you can do, right? But there's actually some work going on in extending it. But if it works for you, it's very efficient, if that makes sense. So if you can use the bulk copy API and it's easy to implement, it's easy to use in your app, it's very efficient to use. It's equally efficient to using TVPs, right? So if you can use it, you should definitely use it. If you're already using it, there's no meaning in switching to something else. Right? But it depends a little bit on how much control you need. Because here, as you see, you can control, I want to send multiple transactions like this, I want to transform the data, I want to do things. You couldn't do that in bulk copy. Bulk copy, you would have to load it into a table and then you do something. And right now, we don't support loading into temp tables on SQL Azure. Okay? So, finally, caching is obviously your friend in any performance scenario. So whatever you can cache, try to cache it, right? But just be aware how long you can keep the cache for and when you should refresh. And that's typically some sort of business requirement. Row versions and checksums, if you do caching, it's obviously interesting to understand, has anything changed? Do I need to refresh the data? And we have two ways of knowing this. One is row version or timestamp, which is basically an 8-byte integer that you can use. So you create a column called row version, and if any column on the row changes, the row version will increment, right? So what you can do then is obviously send a select statement, say, get everything where row version is greater than blah, you'll get everything that's new. And that's an interesting thing with row version. It provides you a high watermark for the database, but you can easily get everything that's changed. One problem to be aware of there is row version will change all the time, so it's not very good to index, right? Because it will always be a very fragmented index, and we'll always have to move rows around, right? Which would be costly. Checksums are good because row version, it's fairly common to have columns that you update all the time, like some sort of state columns, but you don't really care if those changed. But with row version, it's if anything changed on the row, we increment. So if you want to know if certain columns changed, it's better to use a checksum, right? And we have a checksum column function where you can say, hey, checksum over these 3 columns, and then you'll get the checksum value, and you see if the checksum value changed. Then you retrieve the data. You also have a hash bytes function that is slightly more costly to use, but it's much less chance of generating duplicates. So checksum basically returns an integer. So when you hash and return a 4-byte value, you can imagine that there is a fairly high risk of duplicates, meaning there are changes, but you still get the same hash value back. So whenever you use these, and we're out of time, but I'll just show this briefly. So if I have, first of all, I can just show checksum. So you say checksum, and you can say it, I think, on all columns from, let's say, test.accounts. This was apparently the checksum for this column. You can also say hash bytes. And you can actually specify which hash we should use. So MD5 is popular, right? And then it's the values that we should hash. And here, it's actually another new function in SQL is very practical. So here you can't say a column list, right? It's one value. So you could then use concat. And the nice thing with concat is it concatenates strings, right? But it doesn't care about type. It always automatically converts to a string. And if there are nulls in there, it treats them as empty string. So it's very practical to generate these values. So I'll say, okay, concat ID and balance. And that will be my hash byte value. There we go. So there you see the hash byte value as well as the checksum value. So the MD5 is way lower chance, it's more or less insignificant, of getting duplicates, right, for different data getting the same hash out. What you can also do is you can actually create these as computed columns. So I can say in my test accounts table, add hash as this column. And now it's automatically in there, and it's recalculated every time you query. So now you can just say query and get me the hash. So it's defined in the table. And finally, you can also say, obviously now we recalculate every time. We also support persisted columns, which is nice. Now it means we will store the data physically, so you will sacrifice some storage, but we only recalculate on update and insert, right? And this is super useful. Then when you query, this is the final thing. If you're looking for if the row changed, then it's typically actually an update. So you want to update, table, and set some fields. And the dangerous thing with updates is obviously if something changed in between, you will have lost updates. You'll overwrite, which is dangerous. So the safe thing to do then is you say where ID is equal to ID, you pass the ID in, because then now I have an index on ID, right? So I'll find the row very efficiently, because again, I don't want to have index on the hash or the checksum, because it will move around all the time, right? Be costly. And then I just say and my hash is equal to whatever hash I retrieved when I used the value, when I fetched this. And now it will be safe, right? We will not update the row if the hash changed or the checksum changed or the row version changed. Make sense? Yeah, this is, and it's worth, row version is a binary 8. Binary 8 you can cast to big int, which is nice. So then on the client side you can put it in an int64, right, which is just easier to manage than a byte array. But yeah, that's what I had. Hopefully it was interesting. I'll stick around to answer questions, and please fill out the evals. These are some related breakouts today, tomorrow, and Friday that you may want to look at. And I'll be hanging around in the Microsoft booths. And that's also a good reminder. In the booths, the product group is there. So if you have questions around SQL DB, BI, Hyper-V or whatnot, a lot of engineers there that can help answer your questions. Okay, thank you.